Join me in welcome Justin Abrahms, self-taught computer programmer. He's going to share with us computer science for the self-taught programmer. Thank you very much.
Hello, everyone. As he said, I'm Justin Abrahms, and I'm going to talk about computer science for self-taught programmers. A little bit about me. I am a director of product engineering at a company called QuickLeft. We do consulting and also own a product that I work on called Sprintly, which is a project management app. We're hiring, so if you want to talk about that, let me know. I'm also the author of Imhotep, which is a tool that will take static analysis, stuff like PyLint or JSHint, and pipe that into GitHub code review comments. And you can find me online under the name Justin Abrahms. So an overview of this talk, we're going to talk about big O notation, how I learned about it, what it is, how do you do it, and then some wisdom and resources around that. So to start off, I worked for a design agency in New York City several years ago, and this was my first career job that where I was really working on things that were important, and they were important to people, and it was a product that mattered. Before that, I worked for a newspaper, and the things that we did were very quick to start. They had a limited shelf life, and then they kind of trailed off, and it didn't really matter anymore. So examples of that might be like someone's writing an article about AIDS in various counties, and they want a visualization, so you build it, and then the article publishes, and then 3 weeks later, no one's going to visit that site anymore. So I did some work for a ticket seller. They sold Broadway tickets, and my responsibilities were to kind of build the entire thing from kind of an architectural standpoint, and I did the schema design. And to give an example of what a sane data model looks like, you can see here, you have a module, and this module has dependencies on other modules, and there are very clearly defined relationships. And then here was our data model. There was an erroneous requirement laid out, which is that everything had to be related to everything, which is unfortunate because we didn't just have 3 objects in our data model. We had a lot of objects in our data model. And the unfortunate thing about this is that it was really slow when it came time to launch. And this kind of represented one of the biggest failings I've had in my career. And it boiled down to not questioning the requirements given and not really understanding the implications of what I was doing. A coworker of mine, Igor, came to the project after it was deemed very slow, and he said, he was like, oh, of course this is slow, you're doing N+1 Selects. And I was like, oh, that sounds bad, what is N+1 Selects? And so this is what N+1 Selects are. We're going to get a list of posts for this website, and then we're going to loop through those and then fetch them from the database. So we make a SQL query to get some post IDs, and then for each one of those, we make another SQL query to get the rest of the information. And this happened due to abusing Django generic foreign keys, but this was kind of my first introduction into this like N+1 kind of syntax that I'd never really heard before. So I had a few questions, which is, how did I not know this? How did I miss this thing? How did Igor know about N+1 Selects, and I had never heard of N+1 Selects? And then how can I make sure this never happens again? It was very interesting because it identified a gap in my knowledge. And so I guess that begs the question of what is big O notation? Well, big O notation describes limiting behavior as a function tends toward infinity using simpler functions, which means absolutely nothing to anyone unless you already know everything about big O notation. So big O notation is how programmers talk about how the 2 pieces of code relate in terms of performance. And this was really important when I went to my interview at Google. So in prepping for this interview, there was a study list I had. needed to know data structures and algorithms and system design and Java stuff and concurrency stuff. And you'll notice that big O is not on this list. These are the big O items. No one sits you down in your interview and says, here's a function. What is the big O notation of this function? It's kind of assumed knowledge for these topics. And this is kind of how you express your knowledge in those topics. And so it's probably worth talking about a brief overview of data structures and algorithms. A data structure is how you structure your data. It is kind of how you organize things. And kind of an oversimplification would be, if Python didn't give you lists and sets and dictionaries and it only gave you object, how would you build lists and sets and all that other stuff? That how is data structures. And algorithms are a step-by-step procedure for doing a thing. So an algorithm for making a peanut butter and jelly sandwich would be just the recipe. It's the instruction set of how you do a thing. Algorithm is also one of those words that makes you sound super fancy to people who don't know that it just means recipe. So let's talk about big O notation. This is kind of what big O notation looks like. There is an O function. It is a big O, and it has a few things that can go inside the parentheses. So the types of big O that there are O of 1, which is how you read this, O of 1, which is called constant time. O of log n is logarithmic, O of n is linear, O of n squared is quadratic, and O n factorial is factorial. And there are more than this. These are the main ones that you're most likely to see. I'm probably not going to talk about O of n factorial because it's a little, you see it, but it's not super easy to graph, and I have a few graphs in here that make things make sense. And if your math class was a little long ago, like it has been for me, you might not quite remember what these things look like. So this is a graph of the various complexities, which is kind of what you talk, runtime complexities, which is kind of how we talk about big O things. So n squared is the line in blue that goes up really quickly. O of n is red and kind of increases in a flat line up and to the right. The green line that you can see just above the orange line is log n, and it grows faster than constant time, which is the yellow line, but not by a lot, and certainly not by as fast as everything else does. So the axes being involved here are time is the y-axis, how long something takes, and the x-axis is the number of items input into the function. So if you had 5 items and you gave it to a function that was O of n squared, which is the blue line, you kind of track this up and you can see that it's maybe 35 units of time, however we want to measure time. But if you were to pass it to the same function on the orange, it would be 1 unit because it is a constant amount of time no matter how many items you have. So let's kind of go through some examples of these time complexities. This is an O of 1 function. It is fetching something from a list, from an array by index. And the reason this is constant time is because it doesn't matter if the index into the array is 5 items big, the array is 5 items big, or if it's 500 items big, it takes the same amount of time. And this makes a little sense when you have a kind of conceptual understanding of how arrays work, which is that they're all memory offsets into some block of memory, so to say. And going from block 18 to block 20 is no different. It's the same physical operation in the machine. O of n is kind of canonically a for loop. For loops mean it's an O of n thing. Or that instruction is O of n, where n is the size of the thing you're looping over. So this is a function that checks whether something is contained in an unordered list. So we loop over the list. If the thing we're looking for is the thing that we have found in this current iteration of the loop, we return true. Otherwise, we return false. So you might be asking, I see the for loop, but wait a second. There's other stuff going on in that function besides just a for loop. What happened to all that? Are we not counting it? So let's kind of break down this function. As I said, the for loop means it's an O of n operation, where n is the size of the LST variable. Checking whether an entry is equal to the item we're looking for is constant time. You can kind of think of this as comparing two numbers. That's the simplest version. Detecting whether 1 is equal to 2 should be the same speed as checking whether 1 is equal to 2,000. So it's not dependent on the size of the thing you're giving it. And then the return true is a constant thing. It doesn't matter what you return, it's the same speed. So that gives us O of n times O of 1 plus O of 1, right? So we add up all those things. So the next question is, why don't we just say O of n times O of 1 plus O of 1? And the answer is that that's really painful to say. Like no one wants to say, oh, that function's O of n times O of 1 plus O of 1. And for a better answer, we have to go back to kind of the formal definition. And if I were to translate that into non-mathy terms, what that means is that if we plot our function, we can also plot another function, which is m, which is some constant that we make up, times the big O of the function, and all values to the right of that function we should be under. So we have two lines, and those lines should never cross going further right after a certain point. And I'll kind of break this down. So the question is, how do we plot big O? Okay, so we have big O of n times O of 1 plus O of 1, and we're going to plot something. So O of n always means x in our graphing, and that's because it increases over time, and we want to see how this function changes. The amount of time it takes changes over time. So we substitute x for O of n. O of 1 is a constant. It's constant time, so you can pick any constant. I picked 5 and 9 because they make the graphs easier. So now we have the two plot of x times 5 plus 9, which looks a bit like that, just a straight line going to the right. So if we were to, if this is truly O of n, then we should be able to multiply O of n times some constant, and this blue line should stay under the new line. And so here is plotting with a constant of 10. So this is a line plotting 10x. And you can see that this blue line is never going to cross that red line after about 3. So we can say that this function is O of n for all values greater than 3. So that's how we know that O of n is correct. So you might be curious of what some counterexamples to this are. So let's ask the question, is this O of 1? O of 1 means, or constant time, right? Constant time means that we should be able to plot some constant number that stays the same regardless of the x value, where here x is equal to 15, so we're plotting the line at 15. And you can see that the blue line is, in fact, above this red line. And because of that, we know that this is not a constant time function. Okay? So the next question is it the next higher complexity level? Is it O of n squared? And you can see here for values greater than 7, that blue line is never going to cross this red line because that red line shoots up very quickly. And so this is plotting x squared as the red line. And you can see that, yeah, actually, for values greater than 6, this will never cross. So it is true that this x times 5 plus 9 is an O of n squared operation. It just also happens to be an O of n operation. So that's to say that it is true to say that something is a higher degree of complexity. It's just not the best answer. So that would be like saying the number 10 is greater than 5. Yes, but it's also greater than 7 and 9. It doesn't make any one less true, but kind of gives you, you really want the lowest number that you can choose there. So big O is an approximation of algorithmic complexity, which is to say that big O is kind of how you approximate how complex something is, or how much time or how many operations it will take. So let's get back to the code. We still have the same code as before, but what if the list is empty? If the list is empty, then we're going to return false immediately. But big O notation deals with the worst case performance of something. Even if it's empty, we want to know how bad it could be if it had 10 items in it. And there are other big O flavors for that don't deal with the worst case, but we're not going to cover that because it's not really brought up as often in kind of practical use. Okay, so transitioning into O of log n, this is logarithmic time, and we're going to use kind of the same thing as before, where we're going to find something in a list, but instead of it being an unsorted list, we're going to sort the list, and that allows for a more efficient lookup for this sort of thing. And let's kind of discuss why. So we have this list of 10 integers, and we want to see if the number 4 is in there. How binary search works is we choose a center point in our list, and then say, is 4 equal to 6? Well, no, 4 is not equal to 6. So because this is sorted, we can rule out everything in an index higher than the index 6 was in. So we can say that everything bigger than 6 is not going to have 4 in it because it's all sorted. So we split again, and we see, is 4 equal to 3? No, it's not. And so that leaves us 2 numbers, and we check is 4 equal to 4, and it is. This is logarithmic because for every iteration, the sample size that we have to operate on is a fraction of the size, if that makes sense. Okay, so the next one of these is O of n squared. This will make a list of pairs from a list. So this is a doubly nested for loop, and these are the big O. This is the big O for that. So as I said, for loops are O of n, and generating a list is, we'll call that O of 1, and returning O of 1 and appending O of 1. Once we add all these up, kind of in algebra terms, we get O of 1 plus O of n times O of n times O of 1 plus O of 1, which is, again, a pain to say. So let's break this down a little bit. So we can let's rearrange this plus O of 1 and move that to the end. It makes things a little easier. And then we'll plug in some numbers like we did before, where O's of n become x's, and then constants become numbers that we decide arbitrarily. And that once we simplify this, this reduces to x squared plus 29. Okay, so now let's plot x squared plus 29. It looks kind of like this. So if this is truly O of n squared, we should be able to plot some constant times n squared, and this function will never cross it. So here we're plotting 10 times x squared, and you'll notice that the blue line will never cross this red line for values greater than 3. So this does in fact validate that this is an O of n squared function. So there are a few gotchas when it comes to tracking the big O of something. And a big one is that the big O of a function might not matter. If you have an O of n squared operation, and the size of the list that you're going to pass something is 5 items, 5 squared is 25, right? So you're going to do 25 operations. The computers are pretty fast, and 25 operations are basically instant. And so for really small sample sizes, this is not as, it can just not matter. Like your computer might be fast enough that you can just ignore the big O of something. Another gotcha is that the theoretical speed of something is different than the actual speed of something. And as we've said that constants, you get just to pick a number when you're graphing it. The reality is that those numbers might be really large. And so you might have a constant that always takes 200,000 operations to do something, but it doesn't matter how big the list is, it just always takes 200,000 operations. So you could have constant time operations that are slower than your O of n squared operations, because as we said, in a sample size of 5, you have 25 operations. It's dramatically less than 200,000. These numbers in practicality might not pan out. And the other thing is that this is probably not going to make your app faster. A lot of the performance bottlenecks that come in most applications are kind of tied to input-output operations, so like speaking to a database, writing to a file system. Those things will often dwarf the speed of any particular operation. One exception to this is kind of CPU-bound stuff, and changing which data structures and algorithms you use is probably going to make that difference, which is kind of where Big O comes in. And while this is not going to make your app faster, it is going to make your learning easier. And it's going to make, especially as you get into data structures and algorithms and that aspect. And it's also going to make your code review criticisms more articulate. So you can say that this is bad code, and this is bad code because this is an O of n squared operation, and you can instead use an O of n operation, which is better. So let's look at some resources that you can look at for continuing. This is the Algorithm Design Manual by Skena, and it is a fantastic book. It is the first quarter of the book is an overview of Big O from a more mathematical perspective, data structures, and algorithms. And the last 3 quarters of the book are, so you have this problem. You want to sort a list of integers. Well, here are some ways you can do that. These are the runtime complexities of them. Oh, are your numbers all less than 100? Maybe you want to use this other algorithm instead, which is a little faster if you have that one special case. This is a really great book, and I recommend everyone take a look. There is a Coursera course run by Stanford called Algorithms, Design, and Analysis, and they go over a lot of this graphing things and how to how to do that. And it's a good course. It has a lot of math stuff in there. So when I was going through this course, I also had to kind of read up on the math, so it was a little slower. But it's still a really great resource. I'm also in the process of writing a book called Computer Science for Self-Taught Programmers. So that might be of use. It's not released yet, but if you message me, I'm happy to let you know when it'll be available. So you might be asking, how do I write my code differently now? The answer is that knowing Big O doesn't make you writing your code any differently. Because let's face it, we're mostly coders in here, and if you needed to know it to write your code better, you'd probably already know it by now. But the thing that this is useful for is it's the baseline knowledge for data structures and algorithms. And data structures and algorithms will make you write your code differently. And also, this is a communication tool, similar to design patterns, which you informally use but don't know what you're using. You don't know what to call them. It's a vocabulary that you can use to make your life easier in communication with other programmers better. So to kind of recap, Big O is useful in communicating about the complexity of your code. It is just basic arithmetic and algebra. It's used in talking about algorithms and data structures, and it's not as hard as it originally sounds. So thanks. I'm Justin. If you want to hear more about this book I'm writing, or Imhotep, or Quick Left, email me, tweet me, find me at this conference, and I'd love to talk to you about it. Thank you.
Just a few moments for Q&A. There's a microphone over here in the corner if you'd like to ask a question. Or, sorry, aisle here.
How do you know which operation to use when you're constructing, whether you're multiplying or adding the orders in your algorithm? And also, I see a lot of algorithms that get listed as n log n. How different is n log n than log n?
Okay, so I'll answer your second question first, which is how different is n log n compared to n or log n? So if you remember the graph from the beginning, which let's go back there. N log n is n times log n. So n is this red line going up and to the right. Log n is this green line that barely increases above constant. So it's a little slower than, it's as the difference between n and n log n is the difference between this constant time orange line and the log n, right? So it's actually n times log n.
It's almost n.
It's almost n, but not quite. It's a little slower than that. And the first question was how do you know what numbers to plug in?
Well, how do you know which operations when you have your algorithm and then on the next slide you say this one's plus, and how do you know whether to add or multiply the orders?
Okay, so the question is how do you know whether to add or multiply in these items? So this the first O of 1 operation here, if entry is equal to items, is done once every time for the for loop. So it happens one time times the number of items in the list. So you can kind of view everything that happens inside the for loop as being in parens and saying like this number, the size of this for loop, times the number, whatever's happening inside. And then again, if we kind of advanced up to the n squared operation, we have this for loop with inside is another for loop. So we have this n times 1 because the for I2 in list, we do one constant time operation for each item in list, right? And then we multiply that by the numbers in the first list. So that's how you know where the numbers come in.
And then the things that only happen once, order 1 are just added.
Yes, so at the beginning and the end, the things that are just done once are just added.
The equality operator itself is another algorithm, so that could have not O1 operation time. If it's a string, for example, it might be OM or length of whatever that string is. So
Yes.
for your integer example, I think that's O1, but for other object types, it may not be.
Yes, that is true. Thank you. I think it's probably worth mentioning that I'm by no means an expert in big O notation. This is kind of practical big O. There's a lot of intricacies, and people who really know big O well from a theoretical perspective might have some quibbles about how I presented it, but this is enough to pass a Google interview and enough to be able to speak about it in a way that makes you not seem crazy. So hopefully that colors this a little bit better.
What's your favorite tool for actually evaluating the speed of the function?
IRC is my favorite tool, and asking people, I think this is this, let's talk about it, because I don't know of a tool that will just spit out the answer. So it's a lot of looking at this and saying, okay, so pair list equals new array, or new list. What happens when we build a list? Well, we probably allocate some memory, and then that memory we allocate is probably the same size no matter what we do. So I'll just call it constant. And then you ask someone else, and they'll tell you. It really boils down to having a really solid understanding of what the heck your code's doing. And so like when you're building an array, what is actually happening? The knowledge of data structures and algorithms help you because they will tell you, oh, you're doing an insert into an array. Well, inserts into array have a worst case performance of O of whatever. And then you can say, oh, well, I'm going to add something to an array. Let me look up in this data structures documentation, what is the big O notation of it?
Let's give Justin another round of applause. Thank you very much.
Thanks.